The topic of discussion today is inserting business logic security checks into DevOps pipeline. My name is Chetan Kanaki. I'm the founder and CTO of ShiftLeft. So let us start this webinar by asking an overarching question. Do criminals on your website behave differently from typical customers? When I say website, I actually mean web application. And in that web application, there are essentially three security properties that should be preserved: input validity, state integrity, and logic correctness. The failure of web applications in meeting any one of these three properties is the root cause of vulnerabilities, albeit either direct vulnerabilities or business logic flaws that lead to successful exploitation. While a significant amount of research, solution, and attention has been given to code-based and syntax-based attacks on web applications, such as SQL injection and cross-site scripting, deserialization, etc., there exists another class of attacks not easy to categorize or classify and can be seen more of an art. These attacks has been referred to as business logic attacks. And in the course of the next few minutes, we will be emphasizing and speaking of business logic attacks, both from a definition perspective and also use cases to guide our thinking. But before we start, let's go ahead and actually define what a business logic attack is, or what does it mean. So from a definition standpoint, as quoted by Fonneman Institute, business logic abuse results when criminal uses the legitimate pages of website to perpetrate cyber attacks, hacks, or fraud. Let us attempt to deconstruct this definition. As a great number of business processes move into web-based technologies, web applications have become the primary system for effective business process over the internet. Business logic abuse is the ability of these web applications to manage important functions like user interaction, application security, and state performance, which essentially gets compromised. As business processes are specific to a particular organization, such attacks are also peculiar to that specific targets. Business logic attacks are becoming more serious issue of late as they're deeply tied into the company's business processes, meaning it is very specific to the business domain that you're operating in. To combat such attacks, an understanding into the complexity of the logic flaws and the methods of attacking these vulnerabilities need to be investigated. So let us understand how our existing protection measures are attempting to address this particular new set of attack patterns called as business logic flaws. Of course, we use code analysis or code scanners in our early stage of our DevOps pipeline. We deploy web application firewall and intrusion detection systems at the edges or endpoints to protect from threats. But let us quickly examine each one of these from its functional standpoint, starting with security scanners. They are squarely focused on pattern-based vulnerability discovery influenced by untrusted input. This means that when you are analyzing an open redirect type of vulnerability, you're always looking for a 3xxx HTTP error code. Or perhaps when you're dealing with SQL injection, you're looking for a certain set of pattern that would lead for that exploit to manifest. But when we're talking about application logic vulnerabilities, there are no patterns, period. Now let us shift our attention to web application firewalls. While I don't doubt that WAFs or web application firewalls can help stop some type of business logic attacks, I hesitate to accept that it's a good return on investment once you cross a certain level of effort. Not only do you have to heavily customize the WAF for each application it's protecting, you also have to potentially reconfigure the WAF anytime those applications are changed. It becomes yet another piece of software that has to be continuously developed, reconfigured in parallel with your applications. And if you do not have an autonomous system and have a human configuring these policies, it is inherent burden that leads to drift, which means that at some point your WAF always falls behind. Lastly, intrusion detection systems completely lacks context of the application and cannot effectively differentiate between a legitimate user or a business logic abuser. To draw a line of sand, we need to understand what is and is not a business logic flaw. So let's use a few of these salient points to guide our thinking. To illustrate what a business logical flaw is not, it is not a code-based flaw. It is rather a logic-based flaw specific to your business line. It is not malicious behavior of your application. It is the legitimate business workflow used in a malicious way. It is not about what code is written. It is about how code workflow is defined and written. And lastly, it is not about what an application does with the input. It is about how an input triggers a sequence of actions pertaining to a prescribed workflow that you have defined to cater to your business. As we mentioned before, the most important thing when you're looking at for application logic vulnerabilities is to understand how an application works. To do so, it is essential to know the application workflow in itself, like we illustrated earlier. Most of the application's functionality could be discovered just by navigating through the application. For this reason, attackers commonly use a technique called as spidering to navigate and conduct their first process, which is called as discovery. The basic idea of spidering is to extract all the links, internal or external, from your application perspective as your application interacts with those resources. And through this discovery process, the spider would discover entry points, exit points, hidden resources, redirects that are happening in scope of that discovery. Specifically for the application logic bugs, it is necessary to put effort into following special zones where there is more interaction. Now let us double click into these zones, or what we effectively call as points of interest. As we write web applications, they're comprised of web forms, which are essentially serving different functions. Functions like user registration, password recovery, and as we are interacting within the scope of the session, we declare tokens, hashes, and share information in scope of session. Starting with forms, it is not where the approach to inject something into the fields, but in order to understand what is happening with the data is entered, how it is processed and stored, that matters. And specifically speaking of user registration, one of the important sections is to look for whatever is related with user management. Trying to understand how the application registers the user, how it determines the profile, and whether it has established authorization levels pertaining to that user role. For example, if the application identifies a user by groups, or if it identifies a particular user based on an external service, such a single sign-on validation happens as the application communicates with that outbound resource, like your LDAP server. So all that information is essentially trickled upstream for this malicious entity to understand how your application is communicating with these resources. Speaking of password recovery, it's one of those flows that is most valuable from an attacker perspective, because often they induce or trigger a password recovery or reset, and thereafter understand how your application is dispatching an email to communicate with the user. Now, this email could be served with a template that your engineers have defined with placeholders. Now, these placeholders could be injection points for the attackers, where they could effectively induce a command injection and extract more data than necessary. So after mapping out and discovering the application workflow, the next affirmative step is to intercept these flows to identify if certain inputs can cause circumvention of flows to abuse logic. Let us start with user input based or pertaining to requests, where on a form there's several fields, and typically when these fields are filled as they're being interacted by either your consumers or malicious entities, a request is formed, and eventually that request is submitted to your web server. Now, these requests take shape in different schemes, either as GET requests or POST requests. And all of your necessary parameters, cookies, environment variables, and tokens are packed pertaining to that specific request scheme or in the appropriate HTTP header. The next section is outbound communication channels, identifying how your application internally is using services to fulfill workflow conditions. You might be using an external email service provider like SendGrid, so your application might be communicating outbound to trigger an email dispatch. You might also be using an SMS service like Twilio in order to enable mobile communication. Or perhaps if you're using a payment gateway to fulfill your orders at some portion in your workflow, there could be an HTTP or HTTPS redirect to that payment gateway in order to authorize and capture the transaction, leading to fulfillment of order. And finally, all of this transaction is codified in your application using naming conventions. Often as engineers, we choose very prudent and effective naming conventions, where if you're dealing with databases, we typically prefix database, and if it's specifically SQL, we say SQL, or following the RESTful nomenclature, we might say read, update, delete, etc. All of these tend to become cues for attackers, where they understand that your application is actually communicating and writing to a SQL database, or perhaps reading from it, communicating outbound to an email service, etc. So these tend to become interesting cues for attackers to take forwards. So let's further guide our thinking using some real abuse use cases, starting with a typical online auction, which was abused not too long ago, where if you typically examine the workflow with an online auction, a consumer creates an account, participates in an active live bid, and continues to counter bid till he wins and claims that particular transaction associated with that property he's bidding for. Now, if we switch context and examine it from a perspective of an hacker or an attacker might register as a normal consumer, participate in a real-time auction, albeit bidding at the lowest price. Now, if the real-time bidding is occurring and that particular web page is being refreshed constantly, you might have the user names who are also participating in the bids displayed. And often usernames could be email IDs. So this could be a cue for the hacker or malicious entity to collect these usernames, harvest them, and then essentially conduct brute force attacks by inducing password resets with these usernames. Now, as a consequence, typically password resets have a threshold on number of attempts. And once that threshold is exceeded, the natural next step is to lock the account and invalidate any active sessions. So this was a real case where a hacker identified this flaw, induced a brute force password reset on all the other participants on the real-time bid, leading for all their accounts to be locked, their sessions invalidated, and him winning the bid at the lowest price. Switching context, let us look at information disclosure. With any subsystem, albeit a health record-based system, or perhaps an e-commerce system or a banking system, we effectively receive acknowledgements of our claims, orders, and transactions. Often these acknowledgements are sent as emails, and these emails contain links that essentially point us back to our order status or our transaction ID information or summarization. So there was an incident not too long ago, almost in 2017, associated with Molina Health and Signet Jewelers, where an email was dispatched carrying details associated with a fulfilled order. But this email contained a URI redirecting the user back to the detail which was hosted on the web application portal. But note that the flaws that existed in this situation was that no authentication was required for the user to view his details or his or her details. Even worse, the order and claim ID was predictable because they literally carried the primary key or a sequence ID from the database, which was represented in the URI, which means a particular user can literally guess what the next sequence might be and cross over his tenant to access order, claims, transaction information of any other user, leading to information disclosure. The third use case that we'll speak of is something that happened in 2017, where Apple filed a class action lawsuit on a particular vendor who was repairing iPods. Apple's warranty repair program for iPods allowed customers to receive replacement units before the original non-functional music player is returned. And all they required on their portal was a serial number of the non-functional unit and a valid credit card so that they can authorize $1 to identify that this user is a legitimate user along with the shipping address. So this repairman in question figured out how to guess iPod serial numbers based on a formatting algorithm used. Essentially, it was the color of the iPod shuffle, a certain prefixed serial number, the particular manufacturer ID, etc. Given that he guessed it, he effectively managed to predict the next series of sequences and then went about purchasing stored value Visa gift cards in order to satisfy Apple's $1 pre-authorization requirement. As a consequence, Apple essentially shipped 9,000 iPod shuffles to this individual who essentially sold each one of them for $45 in the secondary market. Fortunately, this perpetrator was identified, caught, and a class action lawsuit was also resolved. But note that these three cases that I spoke of have interesting traits that don't smell like vulnerabilities, traits that essentially enabled these perpetrators to identify ways to circumvent business logic flows or flaws in the application. So the main purpose of this webinar is to give you a sense of how we can go about preemptively identifying for those symptoms, because we touched on a few points. One is you of course cannot detect all of such flaws in real time with defenses at the edge, because those defenses should be trained. If you release your application multiple times, those rules should be adjusted appropriately so that it can effectively enforce and protect. The other point that we raised is these flaws are very pertinent to the design of your application, which means that you need an expert guided system so that you interactively ask questions and identify if such flaws exist. We also touched on this point that these flaws are not vulnerabilities, which means that they're not just patterns influenced by untrusted input that cause a condition that manifests as an exploit. It's almost chaining multiple such conditions together, and once chained in unison, evaluating to see if they exist, leading for a possibility of a business logic flaw. So shift-left Ocular is one such tool which lets a security analyst, AppSec teams, and developers interactively investigate to identify violation or lack thereof of adherence of design principles that could lead to business logic flaws. This interaction is aided by a powerful query capability to identify and ask questions pertinent to your specific business domain, whether you're operating in finance, healthcare, or e-commerce. Eventually, when you ask questions, you get answers, and these answers are flaws that violate a certain principle. Now, obviously, you want to take these questions, craft them as policies, enforce them so that they're continuously evaluated release per release. And if it violates, you effectively then decide whether this particular version of your software should be released or not. Obviously, the other question that you also would ask is you'd like for such a system to integrate with third-party systems like Jira, GitHub, where predominantly engineers, developers, AppSec teams spend most of the time in. So Ocular provides the facility to integrate into these systems within the scope of your interaction and investigation, or when you run it in autonomous mode as well. Without further ado, I'd like to buckle up and let us navigate and understand how we can suss out these details using some simple use cases with Ocular. And note that you can even go into advanced use cases as well. But for sake of this webinar, I will illustrate a few simple use cases. To guide our next few use case using Ocular, I'm going to use a project that is open source. It's essentially available at this moniker, which is github.com/conneqc.tarpit. This project is fraught with vulnerabilities and business logic flaws and is available for anyone to navigate with once you get started with the trial of Ocular. What I will do quickly is shift into my console to guide the next few steps. Like I mentioned, I will be using this project called as Tarpit, which is available on GitHub. I'm going to quickly switch to my console. The first step that I've done is clone this project and essentially build to create an artifact. Given that this is a Java project which is deployed on a Tomcat servlet, what I've effectively done is created a web archive as a consequence of building or initiating a Maven build. Ocular is a command line interactive tool that takes as input a particular proprietary format called as code property graph, which essentially is a graphical representation of your code. This graph essentially encompasses the custom code that you write, the open source it consumes, and the framework upon which it is deployed. Think of it as a graph of graphs. Having this graph enables us to effectively understand information flow and thereafter ask interesting questions to see if there's certain business logic flaws that can be triggered on these information flows. So as a next step, I'm going to create this graph that I just spoke of. Typically, it takes less than 10 minutes to create a graph in association to an application being analyzed containing over or approximately 500,000 lines of code. But if you're writing very tiny microservices, which is very optimal and the typical modus operandi these days, it takes less than a minute or perhaps less than 2 to 5 minutes to create this graph. Note that it took literally less than 10 to 15 seconds to create this graph because my application that I'm demonstrating today is fairly simple. Ocular is a command line tool, and what I'm effectively going to demonstrate today at this moment is using Ocular in investigative mode. But you can expand the scope and use Ocular in an autonomous mode as well, meaning take your insights, create scripts and recipes, and bolt it into your continuous CI/CD pipeline so that these evaluations are conducted constantly on a release per release basis. So on starting up Ocular, now I effectively have the ability to ask questions over this graph. But before doing that, I'm effectively going to load a set of recipes that I often use. And by the way, we provide you a set of recipes, batteries included, which essentially contains different patterns of business logic flaws, backdoors and rootkits, and common vulnerabilities. So right off the bat, you get value without even writing a single line of code pertaining to your recipes. The language used by Ocular for interaction is a meta language, which is essentially based on Scala. So if you're familiar with Java or Scala, it feels very native as you interact with Ocular. The first step that I'm going to conduct is load that particular graph that we spoke of or just created at the moment. As this graph is loaded, it enables us to ask interesting questions over this graph. And just to quickly demonstrate, I'm going to execute a particular command which enables me to get all hard-coded literals in the code. Now, this is just a simple command, but it has very high value because I can go one step further and ask if the engineer has mistakenly hard-coded any credentials like AWS secrets, AWS tokens, GitHub access tokens, etc. The other interesting value that can derive of Ocular is you can identify your software composition encompassed in your application as well. Now, Ocular just does not give you version dependent pairs. It can also go one step further in letting you know whether you're using any vulnerable open source library in an unsafe way. So this greatly helps in prioritizing what needs to be addressed from an open source software composition analysis standpoint. But what I'd like to do now is quickly give you a glimpse of the first use case that we're going to traverse. This is a use case called as a denial of service attack on a resource. This is often conducted as an exercise by attackers to identify if your application is consuming a resource without releasing it. That could effectively lead for the application to crash due to resource exhaustion. This example that I'm effectively going to use to illustrate this point is using a global database connection that is initialized in a HTTP GET request path. But note that as this global connection is initialized, the highlighted patterns indicate that the engineer is not using a connection pool, first of all. Even worse, the connection that is established is not being released after the request is serviced. So these two patterns collectively, when chained, would lead to a denial of service attack, where if someone repeatedly hits this web route or triggers a particular form leading to this web route, it would lead for the connection to continuously be consumed, eventually leading to exhaustion. This is a very simple example, but you might have other resources. You might be using a Redis cache, you might be using your file system, and the different ways to trigger certain paths leading to resource exhaustion. I'm going to switch back to the console to illustrate how we can use Ocular to identify this condition. Firstly, Ocular lets you configure different sources and sinks, because from your application standpoint, you might be using different types of resources like database, caches, file systems, other microservices. So what you get is a set of different sinks that we already bootstrap and batteries include as a set of our policies. So here I'm asking using a very simple succinct API for any database connection used throughout the application. So here I've got a confirmation that this particular servlet is using the database connection. The next question that I can ask is whether if the connection is initialized, is it being closed? Because there is typically an API available by any database driver that you used. like java.sql.connection or Hibernate or iBatis or JPO or JDO. So we have codified for all of these APIs and annotated them. So when you ask a simple question like this, we effectively look up your application, identify what type of database driver you're using, and thereafter go further to check whether you're closing that database driver appropriately at system exit or at the exit of the particular function in your application. Finally, I use that same succinct API to ask whether you're using a connection pool in your application, because if you're not, that's even a worse position that you're at. So again, all of that is batteries included and codified. So if you effectively just ask a simple question, you get a true or false. So we've asked 3 separate questions, but like we discussed, it has to be chained together to materialize or manifest a DOS attack. So what you can effectively do is take these 3 questions, bind them together conditionally in a script, and then assert to let your build system know that we need to fail this build because all these symptoms exist in unison that would lead for a DOS attack to manifest. Now let's switch context to another type of use case, which is enforcement checks. We spoke in one of our use cases that I illustrated, particularly pointing to Molina Health and Signet Jewelers and Citibank in 1999. An email was dispatched with the order status. The order status was supported by a route called as order status in the web application. This order details or confirmation details or transaction details was displayed to the consumer without authentication, which led for that consumer to become adversarial, cross over his boundaries into other customer tenants and ask for their order details. So here's a quick example of enforcement checks, where if you have different web routes supporting REST APIs or your web APIs, the question that you'd like to ask is whether, if any of these web routes are triggered, are they being redirected to a login page? Or perhaps looking for an access token so that you validate that particular request is initiated by that specific user who wants to look up his data or her data. So here's a quick example of a very simple web route, which is get order status. Note that the highlighted portions indicate that there is a redirect to login, and once the role is identified, then the next step is to look up the customer's details by effectively referencing the database. Again, this is a very, very simple use case. So I'm going to switch again to the console to illustrate how we can navigate and identify for that use case. So Ocular understands information flow. So from an information flow standpoint, as we looked at this highlighted portion in our slide deck, I want to draw your attention to a couple of things. One is you have input injected, which we typically treated as untrusted input from an external entity. Now, there is a redirect happening to a resource, and then a conditional check there after the redirect to validate that condition, leading to the next step, which is looking up the database or looking up any other resource. So I'm going to conduct this simple inquiry using Ocular to identify, first of all, if we are receiving requests from external HTTP sources, and thereafter touching any database to conduct inquiries. And in this case, we have codified various types of database drivers under this global SQL injection 6. The next step I'm asking for is this condition. This is an important point that I want to pause and reflect on, because your conditions could be specific to your business domain. There is no pattern or signature that is common across all business domains. You might validate against an LDAP server, or perhaps look up a basic RBAC system, or conduct odd zero based validation to check to see if the user is valid. So this is where you bring your specific business domain expertise into Ocular and codify them into the script so that validation is conducted in adherence to what is specific to your business domain. Now, as we define the source, the sink, and the condition, the next question that I'm going to ask is, give me all flows that are happening from source, adhering to that condition, and thereafter touching the sink. So upon executing that command, which is source is reachable, sink reachable by source, give me the flows, but branch point, meaning only if the condition is met. What I get is an entire flow pattern. Now, this is a pretty printed representation of that flow pattern. Note that these results can be delivered in a JSON format as well, and you can apply necessary conditional checks upon that flow so that you eventually take those conditional checks and then influence your build, meaning you say that here is one of the requests among the 20 or 30 that is not doing authentication, which means some consumer can touch this and conduct some degree of an attack on it. So this is one way of effectively checking for a series of symptoms chained together in its existence that would lead for a certain type of business logic flaw to manifest. Note that all results in Ocular is often delivered in the format of an information flow. And there is great amount of detail in association with that information flow format. It carries the parameter that is influencing the information flow, like you see cataloged as tracked, and line numbers associated with that is also cataloged as well. And the associated method and the file is also tracked as well. Now, this is just the basic information, but there is more detail to it. Meaning, we also track the scheme, meaning is it a get or post request, etc., etc. And all that can be extracted, if you wish to, as this great detail is available in the JSON dump. I'm going to switch back to our third use case, which is a fairly interesting use case and fairly prevalent use case as well, which is data privacy compliance. As we all know, any code that we write is always subjected to PCI, SOC, GDPR, etc. So when we deal with our consumer information, any information that carries critical consumer data is deemed as sensitive. So it is of our utmost responsibility to treat that data effectively. Treating effectively means we effectively got to encrypt that data, redact that data, or obfuscate that data if we are sending that data on an outbound channel, either to our syslog or a log file that gets carried to our Splunk dashboard, or perhaps gets passed over an HTTPS secure channel to another microservice. Because it's very hard to understand the lineage and provenance of sensitive data in a very complex microservice mesh. Especially when you're getting audited, a simple question is asked, how do you treat your customer data? It's very hard to have an effective answer to that. Even worse, if someone abuses your business logic flaw, they can touch these sensitive data elements. So it is important, first of all, to understand what is sensitive in the application. Thereafter, understand where is the sensitive data flowing through the lifetime or scope of your application. And then you further ask the question of whether this sensitive data is being redacted, obfuscated, or encrypted before it exits the crevice of your application. So let us switch back to the console and use Ocular to ask these questions. The first question that I'm going to ask is, give me all sensitive user-defined types in the application. Now, this is a very core value proposition of Ocular, which is unique, and no other solution can deliver this. Given that we have the code property graph, which is the graphical representation of your code at our dispense, we also have information flow at our dispense. We effectively built a natural language processing layer over these two subsystems that identifies how variables are named in your source code. because often engineers define user-defined types. If you're for sake of simplicity, if you're speaking Java, you define a user-defined type as class. You say class account, class consumer, class transaction. And then each of these user-defined types have attributes like first name, last name, address, routing number, account number. So shift left Ocula has the capability of identifying and looking at the entire type, and thereafter looking at how the type is named. Thereafter, that nomenclature is compared against various compliance bodies, and then that object is scored as sensitive. Note that the results returned here contain system-defined types, library-defined types, which are package-defined types, and even user-defined types. So in the code base, I have a particular model defined, which is called as class user, which I'll quickly illustrate to you in a moment. If I navigate to the code and shift to this particular directory called as model, note that we have a serializable user-defined type that contains various properties like first name, last name, passport number, etc. Ocula and shift left's code property graph has a capability of identifying this whole object and categorizing and classifying them as holding credentials, PII, and location data. This is really interesting because now you have a catalog to dispense. But you want to go further and ask whether any of these types are being defined and used in your code, and if they happen to be leaking outside the edges of your application. So we'll use an example here where I'm picking this user model type as my source and a logger as a sink, because often as engineers, we want to identify and log everything either as info, trace, or debug so that we understand how our application is behaving from a tracing perspective. But often we commit the mistake of logging sensitive data like our user data or AWS secrets, etc. Now, if that happens, and if our data is not obfuscated, redacted, or encrypted, then we are in violation of compliance. So I'm asking a very simple question, and I get a simple flow in return. Now, this flow to me describes that I have my user-defined type with specific attributes being concatenated, prepared as a string, and then dispatched to a logger. And note that on carefully examining what is happening in the flow, it is clear that there is no encryption, redaction, or obfuscation function. Note that what we have done is batteries included provided to you as a customer effective encryption, redaction, and obfuscation functions that are available in the open source community perspective. But note that you might bring and build your own schemes for doing these functions. And if that's the case, all you have to do is augment the policies so that your packages are reined in and evaluated against to ensure that if it is violating that principle or not. Now, these findings are really interesting, but what you'd like to do is take these findings back to your engineers. And as we all know, engineers write code, commit the code in GitHub, and they often like for issues to be filed as GitHub issues. So let's take these findings, log them as a data flow. Thereafter, explode that flow as a JSON feed so that it's more conducive for an engineer to parse and make sense of. Now let's take that JSON feed and create a GitHub issue from our console, because Ocula is essentially providing batteries included integration into various subsystems like I indicated in the past. So I just called a simple API, create issues in GitHub, and from your console, an issue was created into this project so that the associated engineer could effectively act on. Note that you can define your own description associated with the issue and add your necessary detail. All the necessary API function is provided to you to do this function. Now, some of the folks could, in interaction mode, create issues, But you could take this same function that I committed at the moment, encapsulate it into your CI/CD motion, so that every time you release a code, you have an autonomous system, run Ocular, conduct these degrees of evaluations, and then create issues in the appropriate project so that your engineers can track and resolve for. Now let's quickly shift focus to the last use case that I have, which is what we effectively call as encryption compliance. Not too long ago, various companies were impacted with data breaches. Data breaches happen in various ways, but what leads as a consequence is data exfiltration. Now note that once your data is exfiltrated, you might effectively be using different schemes. So if you use a weak scheme, that means someone could effectively exploit your system by unscrambling your encrypted data. Often when you encrypt your password and you use a weak encryption scheme like DES or triple DES, then it would take fewer compute hours for an attacker, or maybe a simple scheme like rainbow tables to go ahead and actually unscramble those passwords. So it is important to apply a mandate upon all your code bases to measure the strength of the crypto scheme used. And if it is using a weak scheme, which is effectively defined by standards like NIST and CVE, you want to take affirmative action to ensure that you apply a stronger scheme. So my last use case that I'll quickly illustrate to you is check to identify if the code base is using a weaker scheme. Again, I ask a simple question, which is, give me all snippets or functions of the code or code blocks that happens to be using or initializing any weak encryption scheme like DES, MD4, Blowfish, SHA-1, etc. And do final is an initialization of that scheme before it is applied to a particular field. So this code base that I indicated prior is actually using triple DES, where an instance is fetched and it is initialized. The next step is to identify if a certain attribute is being encrypted using the scheme, and thereafter either dispatched or persisted to a database or a log file. Now note in this case, I have a use case or a condition in the code where I have a credit card number being encrypted using DES, and thereafter it is appended to a string and logged on the logging channel. So note that I got this flow, and as I mentioned earlier, you can take that flow and encapsulate it into any format of your choice and send it to influence any build pipeline step that you have as well. Note that I've illustrated very simple use cases, but there are various complex use cases and recipes that we have created to identify common business logic mistakes or flaws, most probably symptoms that lead to flaws, and backdoors and rootkits that might be planted or existential in your code that could lead to different classes of attacks and patterns. So lastly, I would encourage the audience to try Ocular on your code. We provide a 14-day full-featured Ocular free trial. It can be downloaded at go.shiftleft.io, Ocular free trial. Currently, the trial supports Java, and at the request, we can provide full-featured, but the current trial version includes certain additional features, or we have essentially subjected few features only. If you're interested in an Ocular proof of concept, please contact sales@shiftleft.io, and we currently support Java, C, C++, C#, and very soon on our roadmap, we will be supporting Node.js, Scala, and Go. Thank you very much for attending this webinar.